Just realized, oh, that's only 20 minutes, so I'll try to start off right away, and maybe I'll skip a few slides, because as usual I prepare far more material. As a theoretical physicist, of course, I like to think about our preferred future, but I also like to think about the most important future. If you look at your preferred future, like maybe you will read science fiction novels and get some ideas, but science fiction authors are usually not physicists. In fact, that's sort of the opposite. They have to do away with all known laws of physics because then their story doesn't work, and they replace it with something else. Usually nonsense, in my view. So the question I like to ask as a physicist is, we know a lot about the laws of nature, much more than the public even realizes. So since you know that, what would be our projection of the future, our view of the future, knowing that you can't get rid of those laws of nature, you have to obey. And I ask myself all sorts of questions. Will humanity be able to go into outer space is one of the very interesting questions one can ask. And I wrote a little book about that, or in the English version is called Playing with Planets. The Dutch version is called Planetenbiljart. I like to toy and play with planets. And among other things, we discuss the possibility of conquering outer space, but also of robots, of intelligent computers and all that. Those are the interesting subjects where, indeed, enormous developments may take place in the future. Other things will be somewhat disappointing. If you look at the laws of nature, they are extremely forbidding. Most laws that are best understood by us are those laws that tell you what won't be possible, the things you can never do. You can never figure out your velocity without looking out of the window to say, I only know my velocity with respect to something else. You can't determine absolute velocities. There's also laws about energy conservation. You can't create energy out of nothing. All concepts of such nature and a lot more, if you take them all together, you get the books of physics that you know about. So how can we then project into the future knowing that many things are not possible? Well, we've learned how the laws of physics work particularly precisely when you stay on Earth. On Earth you can do very accurate experiments about nature, and we figured out very precisely how the laws of nature work on Earth. But one of the amazing discoveries, not only by physicists, but also by astronomers and many other people who do observations of the outside world, they discovered that actually the same laws work in outer space. So look at all the stars, all the galaxies around us. They're at enormously big distances, unimaginably large distances away from us. But the laws of nature there are exactly identical to the laws of nature that hold on Earth. So this helps us to understand the stars and the planets and the very distant objects around us. We found all these things by looking at spectra of stars, by investigating them in very much detail, more than you can imagine, more than most of you will have heard of. You can make lots of observations on stars and planets and discover that in enormous detail everything matches the things we know about the Earth. So the atoms on stars in the Andromeda Nebula that you see here, those atoms behave exactly the same way as the same atoms do on Earth. So we have carbon, oxygen, nitrogen, and all the other elements, they work exactly the same way. This is very important because now you want to fantasize about going to outer space. And of course you can read the science fiction novels, you can look at movies like Star Trek or Star Wars and conclude from there what the future will be like. But that future is very unlike the kind of future which I think I can deduce from the laws of nature that I know. One very unfortunate consequence is that it will take us more than billions of years to reach the first stars ourselves. So we can only send robots. That will take also tens of thousands of years, but at least that should be in principle possible. But to travel to the other stars is something very, very forbidding. However, on the other hand, what can be done is we can travel into the solar system. We can travel to the moon, we can travel to Mars, and even further away. All those things are essentially possible. But the question is how and what can we do? How can we conquer outer space? Now, in science fiction novels, you learn about lots of different ways. One is black holes, or what we call the space-time warp. Somehow space and time are curved. You dig a tunnel in space-time. Instead of flying to Andromeda directly, you go through the tunnel, and then you are there in no time. That's what science fiction authors want you to believe. Unfortunately, if you look more closer at the details of those laws of nature that control curvature of space and time, we know much, much more details about that than they want you to believe. And it was Mr. Albert Einstein who already in 1915 thought about how these laws work, but now we know those much better and much more precisely. And we checked by experiments, by observations in great detail, and we know now very precisely what the rules are about curvature of space and time. So also what the rules would be with what they call a space-time warp, a machine that somehow magically brings you to some other spot in the universe. Well, think of a black hole, and suppose that there were wormholes to other universes. In fact, some of my colleague physicists, they want you to believe that black holes are wormholes to another part of the universe. So you could go into a black hole and then emerge somewhere else. Mathematically, at first sight, it indeed looks like this, and that's how some of these people got into these crazy ideas. But there's a little problem with this, and that is that a black hole will generate gravitational fields which are so tremendously strong that they will rip you apart. And when you try to dive into a black hole, you will be stripped, you'll be stretched in 100,000 pieces before you get close to it. So you won't be able to get there at all. And the question is, why not? Well, there's a very simple rule about that. You have to take the speed of light and divide that by the size of the black hole. Then you get a quantity which looks like a frequency, the inverse of a second. And that frequency tells you that you feel like being in a centrifuge, which rotates with that frequency. If you compute that frequency for a black hole as heavy as the sun, you get 100,000 cycles per second. Because a black hole that would have the mass of the sun would be a couple of kilometers in size, and if you take the speed of light, that's 300,000 kilometers per second. So you get something like 100,000 revolutions per second. If you go into a centrifuge and you rotate 100,000 cycles per second, you will die. Long before that, the centrifuge will break apart. It won't work. So then you can ask, okay, well, we made a little calculation error. What kind of black hole would you need that you can enter safely? Well, the mass, this is the formula, and I don't want to burden you with too much science, but the formula has the mass of the black hole in the denominator. So the bigger the black hole, the slower that frequency is. How big does a black hole have to be if you want that frequency to be no more than 10 cycles per second? That would be pretty painful, but you can survive it at least. That black hole would be 100,000 times as heavy as the sun. So imagine science fiction authors, they have a spaceship with a little warp entrance nearby. Well, that warp entrance is 100,000 times the mass of the sun. So there's a little calculation error that you can't really overcome that easily. Are there black holes such a mass? Yes, in the center of our universe, in the center of our galaxy. In the center of the galaxy, there's a black hole with a mass of about 1 million solar masses. So yes, you could jump to the black hole and not be ripped apart. However, you will die long before you reach that black hole, because there are other stars and planets and gas clouds that also fall into that black hole. And whenever you meet any of these clouds or planets, they'll go with something like the speed of light. So they will kill you. And you will be dead long before you enter into the black hole. And even if you ignore all that, you still ask, would you be able to exit at the other side, so to speak? Well, those rules are much under dispute, but most physicists agree it's not going to be that simple. You're not going to re-emerge anywhere else in the universe. You'll just die. So there's no way we can use that. There was another very interesting theme that I want to show, and that's the use of tethers. A tether is a cable, and with a cable you might think of making a cable that connects the surface of the Earth to a geostationary satellite. This idea has been seriously considered, also by NASA, so it's not totally ridiculous. Physically speaking, the idea is much better than the black hole idea. At least in principle you can do this. And instead of having a rocket ship going to outer space, you have an elevator. The elevator just pulls you up and lets you down. So no big fireworks or something, just a gentle elevator. And wouldn't that be much, much better? It would be a gigantically good idea to have just an elevator lifting you into outer space. There are many science fiction stories based on that. Unfortunately, there are two things wrong about the idea. One is, what kind of cable would you need? You would need a cable that is tremendously strong and at the same time tremendously light. Why? Well, the cable will have to be so long, thousands and thousands of kilometers, that it would first have to lift its own weight. But if it's too heavy, the weight of the cable would be much heavier than the thing that you want to lift. And the cable will just succumb under its own weight. In fact, if you calculate this, you see the strength of a cable has to be multiplied with the length that you want, and then you have to compare that with the mass that your cable would have. That's a little formula to get there. Now, there may be some physicists in the audience, maybe not, but what you get is that the quality of a cable can be expressed in terms of meters per second square. So that's a velocity square. And if you calculate what that velocity is, you find that for a steel cable, that velocity, the steel cable will break if that velocity becomes something like 400 meters per second. That's a bit over the speed of sound. What this means is whatever you make out of steel will not be able to go faster than the speed of sound. If you make a racing car and you make the wheels out of steel, when the racing car will reach that velocity, 400 meters per second, which is very fast, of course, for a car, the wheels will blow apart. The wheels will not stay together. The steel is not strong enough to make those wheels rotate that fast. So that's a limit. Now, chemists have explained to us that there are strong materials. And there's a material called nanotubes, which is pure carbon in a very special arrangement. Those can be made a lot stronger. And then you get something like 7 kilometers per second square. So that's a very much stronger cable. That's what you need, because it's very easy to estimate what strength you need. The quality you need is a cable which can bring you out of the escape velocity of the Earth. That's 11 kilometers per second. So the cable you need would be the square of 11 kilometers per second. That's about twice the strength of a nanotube. But that's good enough. You make a cable very strong only where it's very light, and you make the cable thinner when it goes down. So then you can get around this problem. So the nanotubes would in principle work. Now the second mistake about this idea. So in principle, yes, if you can make nanotubes, if you can make a cable, I think it would be a very dangerous thing if the cable snaps. Then not only the inhabitants of the elevator will die, but also on Earth, all these cables will fall down. But the second thing is more fundamental. You would think that lifting an elevator to outer space is much more gentle and would cost much less energy than this whole display of fireworks that is being used today. But when you do the calculation, you discover this is not so inefficient at all. The question is, what does it cost? How much energy do you need to bring a certain weight, a certain payload into outer space? You calculate that and discover to your surprise that to bring a payload into outer space is not that inefficient at all. Okay, you lose a few factors, a factor of 5 or 10 perhaps, compared to the elevator, but not much more than that. So energetically, it's not so inefficient at all to do it this way. So then I say, why all the trouble and why all those dangers of a cable which might snap? Material might weaken due to cosmic rays, for instance. How do you overcome that problem? So I think we should stick to this method to go into outer space and not try to make space elevators. About colonization, why would we colonize the outer space? I'm talking rather quickly because I think my time is running fast. So why would we colonize outer space? And my science friends say, you know, what are you doing? Why do you send humans to outer space? It would be a waste. We could much better send robots at a fraction of the cost, much more efficient. Robots can do a lot more than humans in outer space. So why not send them? Of course, we should send robots to outer space. And that's what's happening today anyway. So yes, but to send humans, we just do that out of curiosity, out of the expansion, drift. We just want to have humans there, not because of science, just for the hell of it, just because we need to go there. I mean, that's going to be the basic argument. That explains the public interest in this notion, not because the public wants to solve science problems. They just want to go there and see what it's like. And that's ultimately also my argument why I would like to go to outer space. Not because I'm a scientist, just because I'm a human person who likes the idea of people going to outer space. If it happens to be affordable, then we should go there. That's a big if, because going to outer space will be very expensive. Now, I've been playing around lots of ideas, and this transparency I already made before my contact with the Mars One people, and they already emphasized again, so this is where we agree very much, that the media will play a very important role. And whenever someone goes to outer space, the whole world will be watching. So it will be a very difficult event to describe some science fiction novels, where someone might go secretly to Mars. There's no way the whole world will be watching. And of course, we need funds, and we need the fundraisers to be happy. So they want everything to be followed in as much detail as possible. The internet is another factor usually totally ignored by science fiction authors. I think the internet is very important for two reasons. One is for communication, and also for the spreading of information. If there's any problem, you can look it up on the internet how to solve it. And the whole world population might contribute in trying to solve those problems. So the internet is going to be a very, very important factor in going to outer space. And then the remotely controlled robots. I also believe that robots will be perhaps in the precursor of human colonies. And I have reasons to believe that in the not so distant future, robots can really make truly intelligent. Computers won't stop as where they are now. They'll become more and more programmable in an intelligent way so that they show intelligence all by themselves. And I think that's in a not so distant future. Artificial intelligence is on its way to make computers smarter and smarter. My laptop is still tremendously stupid, but that's still something else. That robots in space are advantageous, everybody can see. We have robots in construction works on Earth, also robots in outer space. There are several robots now running around on Mars, for instance. They are there already. But not only Mars, also there's a beautiful machine which is orbiting Saturn this moment, and it has been already for some 10 years or so. It's called Cassini. It is a spacecraft, fully automated, which can watch the moons and the rings of Saturn in enormous detail, and it has brought home thousands and thousands of lovely pictures in amazing detail. It came much closer to the rings than in this picture, and saw all sorts of details there which are really amazing. Those rings are extremely interesting, also I think for future colonists in the late future. Maybe those rings themselves, you can live there, but that's just a wild speculation. If you colonize the universe, why not begin with the closest neighbor of the Earth, the moon itself? Now, for some reason, the moon has not caught the public's imagination. I'm a little disappointed about that. I think, logically speaking, we should first go there to colonize the moon. You can do lots of things on the moon. First of all, people have shown it's possible. People have been walking on the moon, so there's no question about whether it can be done. Even there, you can go back to Earth from the moon. And there are lots of things, interesting things to do on the moon. Of course, you can try to make a human colony. That would be a subject of very much interest for the public in general. You can explore, you can exploit the moon, you can find materials on the moon that can be useful on Earth. Yeah, and you can do science. In fact, you can do lots of science. I mentioned here a number of possibilities. You can make big telescopes which are not hindered by any atmospheric effects. You can study rocks, in fact, even ancient rocks which come from the Earth. Even the life sciences might get interesting science from the moon. You can do low gravity science, low temperatures, and so on and so forth. So there's lots of interesting things to be done on the moon. But So for some reason, people think Mars is more interesting. Indeed, the landscape of Mars is much wilder than the landscape on the Moon. You have mountains there, you have deserts, you have very different landscapes. And Mars is extremely attractive. So you're going to hear a lot about Mars colonization by the next speaker. This I want to ask your attention for. The Planetary Society is an enthusiastic group of people in the United States who also have lots of money, and they are strongly supporting the idea of not only sending humans to Mars, but generally to explore space, and also by manned space exploration. So I think they are an important factor that we should not ignore. And the Mars One project will be handled, I presume, by the next speaker. So I will not say too much about that. Just ask questions where we go from there. And from there we can indeed inhabit the entire solar system. So the solar system consists of lots of planets, and those planets orbit in wider and wider orbits around the Sun. In principle, all could be reached in a reasonable amount of time by spaceships. So we could go into all these places. Now, some of these planets are much too large and heavy. They're heavy gas planets. You can't walk on their surface for various reasons. There's far too much gravity. There is no soil to walk on. The atmosphere is suffocating. So, and the pressures are too high. So it's hopeless. You can't really go there. But all these planets have moons. Or most of them have. And those moons are extremely interesting. And most of these moons are quite inhabitable in principle for humans. So we don't have to stop at our moon. We don't have to stop at Mars. We put all these other moons. How's my time?
So already run out.
I've already run out. So then I think I should stop. Maybe I should mention the time it takes to get there. It's all questions of years. But we might not stop there. We might go to Pluto and beyond, because the fact that these planets are very cold is not such a hindrance. It's rather easy to isolate yourself. These outer planets are made of ice for a large part, and ice is a lovely material. You can build things out of ice. You can get water out of it. You can produce your air, the breathable air, out of ice. So ice is a lovely material to have, and it makes colonization a lot easier. These distant things are actually easier to colonize perhaps than Mars, where it's very hard to find any water. It's there, but it's hard to isolate. On those places it will be easier. So why not go there? And why stop at Pluto? You can go on. There are more very distant planets out there, but more and more difficult to find. Well, I could go on for ages, but I just feel my time is over, and I promise I will only go about 10 minutes after the time is over.